Okay, so what we have here is we have a metal and we have water. So what it's going to tell you is that there's being a metal that's going to be dropped into water. And that would get us this final picture. It's going to tell you the mass of the metal, the specific heat capacity, but it will not tell you the initial temperature of it. For the water, it's going to tell you the mass of it, the specific heat capacity. It's going to tell you the initial temperature and the final temperature. So the only thing we're actually looking for is the initial temperature of this metal. So these two objects are separate at the beginning, then they're being put into one, and we're going to try to find out that initial temperature of the metal. Before we start, it's really important. This is usually what I always do, and actually I sometimes screw it up. We need to find out which one's going to be negative. And to do that, you have to find out which one has the higher temperature. That's the one that's going to lose temperature. So by doing that, what we're going to do, since the water, it tells you the initial and the final temperature. If you look at the initial temperature, it says 21 degrees Celsius. So it's going to start at 21, and when they get mixed, it's actually going to increase temperature. Well, if you're increasing temperature, it is probably going to be a positive value. So it's actually gaining energy. And what that means is the metal has to be the opposite for them to come into equilibrium, which just means balanced. They're going to come to the same temperature. Notice 25 degrees Celsius. 25 degrees Celsius. So in order for them to get balanced, this temperature had to be a higher, or this metal had to be a higher temperature. And so it's actually going to be losing temperature. So this is going to start off higher than 25 degrees Celsius, and then its final temperature will be 25 degrees Celsius. So that helps us for our equation, because what our equation is, in order for them to come into equilibrium, the energies between the metal and the water have to be equal to each other. And so what I'm going to do is I'm going to set them equal to each other. We're going to have Q equals Q. Very important to remember. Metal is negative, so it needs to be negative Q. Okay, so now what we're going to do, since we don't have the value of Q, we are going to expand them so we can work with them. So for Q, you're going to look at your equations. What equals Q? Hopefully you said Q equals MCAT. So we're going to substitute in, instead of Q, we're going to actually change it to MC. You can do delta T, but notice we have TF. So I'm going to actually do MC TF minus TI, which is the same thing. Do not forget your negative. Your negative needs to be out here or else it will mess you up. It is going to be equal to MC delta T. Although notice we have our TF and TI. So what I'm going to do, remember, delta T is going to be just your final minus your initial. 25 minus 21. Delta T is equal to 4 degrees Celsius. I'm just going to do MC delta T. I kept this positive because up here we said it was gaining energy. Okay. So now what I'm going to do is I want to get this purple TI by itself. Notice I'm color coding. Makes it a lot easier if you color code. So first thing I'm going to do is divide by negative MC. That way we're trying to get TI by itself. I'm going to divide both sides by negative MC. Nothing on the right cancels out, because notice they're different colors. But on the left, we get rid of our negatives and our MCs. So I'm going to push the camera over so we can work on it, and I'm just going to rewrite what we have. So we have TF minus TI, and actually I had it in parentheses, is equal to MC delta T divided by negative MC. So all I did was take the information from down here and rewrite it, just so I had more boardroom. Notice parentheses. That means we could distribute something in there. Notice we have nothing to distribute. Technically, if you want, it could be a 1. That way we can get rid of it. So if we multiply them both by 1, we would just have TF minus TI is equal to MC delta T divided by negative MC. So that just gets rid of the parentheses. That way we don't have to deal with them. So what I'm going to do is I'm going to try to get TI by itself. So I'm actually going to make it a positive value. There's more than one way to do this. This is just the way I prefer. So I'm going to add TI to both sides. That looks terrible. And so I'm going to cancel it out on the left, but notice it stays on the right. So I'm going to rewrite this as TF equals MC delta T divided by negative MC plus TI. This solves for TF. Now what I'm going to do, notice this whole term is being added to TI. So I'm actually going to subtract this entire term. I'm going to subtract MC delta T divided by negative MC. What that's going to do is that's going to cancel these out. I would cross them out, but it's going to ruin my pen, and I won't do that. So negative MC delta T divided by negative MC. So this blue cancels out with this, and then the purple is going to cancel out down here. So what I'm going to be left with, it looks like a mess, is TF minus, remember we subtracted, MC delta T divided by negative MC. And it's going to all equal TI. So now all we're going to do is we're going to plug in our values because we know what each one of those are. So TF we know is 25 degrees Celsius. And we're going to do mass. Notice it's in blue, so we should be using everything in blue for the numerator. We're going to have 0.15 kilograms. Specific heat capacity of water. And then delta T, you can either do TF minus TI if you really want to, but I'm just going to do delta T, which is 4 degrees Celsius. You would get the same answer. And then divide by a negative MC. So using our purple, 0.05 kilograms. And then also 899 joules per kilogram degrees Celsius. For your answer, I believe it'll be around 50.8. Just kidding. It'll be 80.8 degrees Celsius. If you did not get 80.8 degrees Celsius, what that means is more than likely you forgot to divide by 0.05 and divide by 899. A lot of times that's just a calculator error, so make sure you do that correctly. You could also get 80.9, so if I actually rounded correctly, that's what it should have been.